Have you ever been scrolling through your Instagram feed and seen a picture of a really, really nice professional studio and asked yourself, why do people spend thousands of dollars to make records in these spaces? Couldn't they just save that money, buy the studio equipment themselves, and then set it up and use it wherever they want? Wouldn't the results be almost exactly the same if they were to do that? So, this is true to an extent. But people are willing to spend big money on recording spaces because of the characteristic sounds that the space itself can provide. But what does that even mean? What is the characteristic sound of a room? How does a room even make sounds at all? Rooms can make sounds by reflecting sounds made within them. As we'll see, these reflected sounds can really be considered as separate sources entirely that can drastically affect the way we perceive and record sounds in an enclosed space. So, as an artist, engineer, or producer, why do you need to care about reflected sounds? When we hear any sound within an enclosed space, we aren't hearing just the source. We're hearing that source superimposed with all of its reflections from the space that we're in. So the space that we're in and the source material are really inseparable in terms of our perception. All we hear is the sum result. For producers and engineers, having a basic conceptual understanding of reflected sound can help you answer a lot of questions in your recording or mixing process. Where should I place acoustic treatment in my home studio space? How should I position my speakers relative to the walls of my room and my desk? Where should I sit in relation to my monitors? How should I position an instrumentalist or vocalist within my studio space for best results? As an artist, having some conceptual knowledge about reflected sound can help you make choices aesthetically when making your next song or album. Answering questions like, what kind of sound will I get if I record this vocal in a bathroom versus in an abandoned warehouse versus outside versus in my normal studio space? All of those places are going to sound different, and if you understand some basics of reflection, you'll be able to have a better idea of what result you will get in each space. So let's get into the details and figure out exactly how reflections work and what they can do for us and against us. Before we can really understand reflected sounds, we first need to understand how sound is generated and propagated through the air. Any sound is a pressure wave acting on a compressible fluid, which in our case is room temperature air, unless you're out there making underwater recordings, which I'm sure plenty of people do. A physical system can oscillate in a wave state when it's subjected to some kind of disturbance coupled with a restoring force. What do I mean by a restoring force? I mean some type of force that acts to pull the system back towards its equilibrium configuration after it is disturbed. For a simple example, think about a block attached to the end of a spring, where the other end of the spring is attached to a fixed wall. If I pull the block away from the base of the spring, extending it, and then let it go, the spring pulls the block back towards its equilibrium position. But the block then has momentum pushing it in the other direction, which will compress the spring, which will then push it back again, and leads to an oscillation of the block's position around that equilibrium point. The block is now oscillating in a wave state where we can describe its position relative to equilibrium with a basic oscillating wave. So we know that sound is physically a pressure wave, but what is the restoring force that allows that to happen? Newton's third law of motion will give us everything we need to understand the restoring force here. When we create a sound, we're fundamentally pushing air particles away from the source. Those particles in the immediate vicinity of our push will feel a force from the particles we moved with our sound. Newton's third law states that that force will have an equal and opposite reaction. So the particles that get bumped into push back on the particles of our initial sound wave, which acts as a restoring force for those particles to oscillate. This type of action is called a longitudinal wave, as opposed to a transverse wave where you might think of, say, a rope moving up and down or an ocean wave. In the longitudinal wave here, the particles oscillate around their equilibrium position much like the block on the spring does. The sound does not cause any bulk motion of the air such as something like wind or a fan would do. It simply sets those particles into an oscillation at the frequency of the source. So now we have a very basic understanding of what actually allows sound to exist in air in the first place. A disturbance in air pressure, such as a speaker or a person talking or an acoustic guitar, sets the air particles in the room into sustained oscillation made possible by the restoring force described by Newton's third law. But because we're working in an enclosed space, eventually our pressure wave is going to encounter a boundary, such as a wall, floor, ceiling, desk, person, animal, whatever. Understanding what happens at these boundaries is critical for understanding how reflections color our perception of sound. When our sound wave meets a boundary such as a wall, those particles are going to get pushed against the wall instead of against other air particles. Boundaries such as these can reflect and absorb energy from these incoming sound waves. For now, we'll discuss reflections and we'll get to absorptions in the next part of this video series. So when the pressure wave acts on the particles near a wall, the wall and those particles will come into physical contact. The air particles exert a force on the wall from the sound wave, and by Newton's third law, the wall then exerts that same force on the air particles in the opposite direction. This is going to alter the motion of those particles and in essence create a completely new sound wave. The push back from the wall or boundary is what creates the reflection. The geometry of the reflections follows something called Snell's law, which also applies to electromagnetic waves and states that the angle of incidence will be equal to the angle of reflection for any incoming wave on a plane surface. Real surfaces are not perfect reflectors and will absorb some energy from our sound waves, but the geometry of this situation is largely unchanged even when accounting for absorption of sound energy. So basically what is happening when sounds are reflected is our boundaries are making their own sounds. They are pushing air back to us with specifics determined by their orientation, materials, geometry, etc. So really, we can consider them as separate sources of sound entirely. For example, a reflection of a person's voice is really the same as a clone of that person singing the exact same line at a distance and orientation away from the microphone equal to the total travel length of the reflection. This virtual source is known as the image of the reflection in the surface. Think of the virtual image of a sound the same way you think of the virtual image coming from a mirror, reflecting light. When you look at yourself in a mirror, the situation is identical to a clone of you standing on the other side of a window, basically. The same is true for reflected sound. If we had no concept of reflected sounds, we would think that these reflections are just other sources of sound. In a rectangular home studio, such as a normal bedroom like the one I'm in right now, there are 6 surfaces we need to be concerned about for reflection, excluding furniture and people and other things like that. We have the floor, the ceiling, and 4 walls around us. My voice right now when I'm making this video has an image or reflected source from all 6 of these surfaces. Then the image of that reflection will be reflected again from every other surface, creating Then the image of each of those reflections will be subsequently reflected again as it moves around the room, creating an exceptionally complex field of sound. In a small room like the one I'm in now, hundreds of reflections can happen every second. So reflections really do play a large role in what we hear and record within an enclosed space. You can easily demonstrate this yourself by moving to different places around your house and outside, and maybe saying the same phrase at the same volume or clapping your hands at the same speed. Even though you're using the same source material, you're going to sound very different in each space because of the reflections that are coming back to you, or not coming back to you in the case of being outside. In general, high frequencies will experience more absorption when encountering a boundary than low frequencies will. Because of this, many home studios and small recording spaces struggle with low-end reflections. Beyond that, different types of surfaces will create different sounding reflections based on their composition, density, porousness. The 2 most common surfaces we'd encounter in a home studio are drywall and carpet, or maybe hardwood flooring. For harder, denser surfaces like drywall or hardwood, not a lot of sound energy is going to be absorbed when sound waves are reflected from those materials. So those types of surfaces are often the most problematic when we're trying to limit reflections or figure out how to deal with them constructively. On the other hand, a surface like carpet is going to absorb a lot of sound energy because it's much more porous. We'll get into absorption in the second part of this series, like I said earlier, but for now, know that a surface being porous will basically trap some of the incoming air molecules as they are incident on that surface, meaning that not as much of their energy is going to make it back out into a reflected sound wave. This is why a lot of people choose to set up home studio spaces in carpeted rooms, because the entire floor will help them in dealing with reflections. For small rooms, like most home studios, reflections that arrive in the first 10 to 20 milliseconds after the initial source are the most important in determining what that room is going to sound like. These are called first or early reflections because they make it to your ear or microphone after their first or an early encounter with a reflecting boundary. These reflections are critical because they have the largest amplitude of any possible reflection. Like I mentioned earlier, each time a wave reflects from a boundary, it's going to lose some part of its energy in that reflection. Sounds also lose energy as they travel through the air Sounds also lose energy as they travel through the air, meaning their amplitude is going to gradually diminish over time. So the first reflections are the loudest because they've had the least opportunity to have their amplitude diminished. When thinking about early and first reflections, you need to keep in mind that it is positionally dependent. Each point in any room or studio is going to have different first reflections. Also, any single point is going to have different first reflections based on the positioning of a source. This concept is very critical in room treatment. Most people choose to prioritize placing their treatment in the spots where first reflections will occur. This ultimately will maximize its impact on the sound of the room. Another very important type of reflection to understand are reflections that are made from corners, such as where two walls meet in your room or where the two walls and a ceiling or floor meet. These reflections are super important because they will follow you or whatever source you're concerned with around the room to any spot. We can easily understand this by recalling Snell's law that I mentioned earlier, along with a simple visual layout. The diagram that I'm drawing here is taking the perspective of looking down at the floor from the ceiling directly above the corner of a room where two walls are meeting. The dashed line is my sound wave, and the arrows on the line represent its direction of travel. Keep in mind, sound doesn't move as a line like this, but this is the easiest way to demonstrate the concept visually. When it finally meets that wall, Snell's law tells us that the angle of reflection will be equal to the angle of incidence, like we discussed earlier. So after the first reflection, our reflected wave is now directed towards the other wall that it hasn't touched yet. Again, the angle of incidence will be equal to the angle of reflection. Thus, you can see in our final resulting wave, it's coming straight back at the source. This holds true for any position, any angle of incidence, any source that is being reflected from a corner geometry. For this reason, corners are also commonly treated places within rooms because their reflections will find you no matter where you are set up. So we've covered a lot here. We know that reflected sounds are made possible by Newton's third law. Reflective boundaries such as walls, floors, instruments, furniture can push back on incident air particles exerting a force on them, thus creating what can be considered as a separate sound source entirely. We also covered two very important types of reflections: first or early reflections and corner reflections. And we know that the reflected sounds drastically alter our perception of sound within an enclosed space. Reflections form the core of room acoustics. Other phenomena such as absorption, diffusion, normal modes, and reverberation all stem from this most basic action of reflection. Having a conceptual understanding of how reflections are created and what paths they will take after reflection can really help us make good choices as artists, engineers, and producers when we're recording, mixing, or setting up our workspace. Try to pay attention to reflected sounds in your everyday environment to really ingrain this information into your memory. How does your voice sound in the space where you're listening to this video? How about other spaces, outdoors? Try them all and just see how they sound. Also, start paying attention to the geometry of surfaces around you that sound could be reflected from, and take note of the qualities you perceive when listening to sounds in that space. Over time, you'll get a better feel and expectation for how a space will sound without ever having heard anything within it, because you've started to pay attention to reflections in general. Eventually, you'll be able to take advantage of these concepts and use them to create better recordings, mixes, and songs. All right, that's it for this episode of Scitone. Thank you so much for tuning in, and I hope you enjoyed it and learned a little bit about reflections along the way. If you'd like to get a bit deeper understanding of any of the things I discussed today, leave me a comment and we can talk about it. Also, if you've got a suggestion for a future Scitone topic, I'd love to hear about it. Take care, everybody, and I'll see you in the next video.